All right, so hi everyone, welcome back from lunch. Good, so we are going to start the afternoon session, and we'll start with Zihan, who's going to tell us about almost optimal sublinear additive spanners. This is on sublinear.
Yeah. So the title contains the word sublinear. Yeah, thank you for coming, and thank the organizers for having me here. Very happy to be here. So this is a joint work with Tianyi Zhang, who is right now a postdoc at Tel Aviv University. I'm Zihan. I'm a postdoc at Rutgers, and I'm starting as a professor at Rutgers too. So, the title is almost optimal sublinear additive spanner, but really the one-line message that I want to convey in this talk is sublinear spanners are almost optimal distance oracles. Okay, so if you forget about everything, you can maybe take this sentence away. What does it mean? What is a distance oracle? It is a data structure that allows you to take a graph as input and pre-process it in whatever way you want. And you get a data structure out of it. The data structure is required to take a pair of vertices, UV, and report approximate distance between these two vertices. Okay, that's what a distance oracle do. Okay, any data structure. Okay, so spanners are almost optimal distance oracles. Optimal in what way? In the sense that it is achieving the best size accuracy trade-off. Okay, so for a data structure, we care about two measures. First, how large it is. Basically, what is the size of the space you are taking? Okay, and how accurate you can report the distance. Okay, sometimes there's also a query time. This is a different measure. A query time is not within the scope of this talk. Okay, so we will not talking about that. We only care about two measures, size and accuracy. And spanners can achieve the best size accuracy trade-off. This is what we're going to talk about in this talk. Okay. So sometimes we also consider dynamic distance oracles. There we also have update time. Okay, all of that measures are not within the scope. It's just size accuracy trade-off. Okay. The third point, almost meaning we're still not exactly the optimal. So we are into a little of one factor away from that. Okay, that is the one-liner information about this talk. Okay, so how many of you know what spanners are? Those, yeah, basically almost everyone. Okay, that's good. So it's just a restricted version of approximating distances. It's a subgraph. Okay, so distance oracles allows you to take whatever data structure you want. And spanners are a very restricted one. I just take a subgraph and look at the distance in this subgraph as the approximate. Okay. So this really means a conceptually simple framework, spanners, can achieve near optimal size accuracy trade-off in this task. Okay, so that's the message. So let's still make sure that we're on the same page. Spanners, given a large graph G, a spanner is a subgraph of G, such that between every pair of vertices, the distance in the subgraph is within some factor from the distance of the original graph. Okay, so let's consider only unweighted, undirected graphs. So taking a subgraph, you can only increase the distance. Okay, so the distance can only increase, but not much more than a factor, for example, defined by a function f. This f is called the stretch of the spanner. Okay, so you can only increase, but not too much, governed by this function f. And there are two typical scenarios which we have considered in the past. One is multiplicative, and the other is additive, basically constant additive. Okay, multiplicative one, probably you are most familiar with it. There's a greedy algorithm. It's allowing the distance to increase by a constant factor. Okay, additive is just a +2. Okay, for example, +2, +4, any plus constant. These are two typical cases that we study for spanners. Okay, so for example, this is a subgraph of the original graph, and these are two vertices. The original distance is 4 if we take the original graph, the shortest path. And the new distance in the subgraph is 6. Okay, this is a +2 approximation in distance. Okay, this is what we require in the +2 additive spanners. The distance can only differ by 2. Okay, so in these two typical regimes, previous research has got a lot of very good results on this. Okay, so the typical like modificated one, it has been shown that if we allow stretch 2k minus 1 multiplicatedly, then the best spanners we can get is n to the 1 plus 1 over k sides. Okay, here sides means number of edges, because we cannot modify vertices at all. We can just fix all the vertices and take a subgraph. Want the subgraph to be small, so number of edges. Okay, and this is tight under Rutgers conjecture. Tight even in the sense that any data structure cannot get smaller than that space. Okay, not only for spanners. Okay, so this is basically a small illustration that spanners are optimal data structure in this case. Okay, this is modificated ones. So additive ones, studies cases are +2, +4, +6. You may wonder +1, +3, +5, where are they? They can be reduced to similar cases. +1 is +0, +2 is +3 is +2, +5 is +4. So they have the same complexity. Okay, it can be shown by some bipartite construction reduction. Okay, so these are the cases that studied in a plus constant additive spanner. For +2, the best bound is n to the 1.5, +4, n to the 1.4, +6, 4/3. These two cases are also proved to be tight for all data structures. The only remaining open case is this one. It's not yet proved to be tight. Some believe it's about the same as 4/3, but not close yet. Okay, so these are previously known results for plus additive spanners. So a very interesting lower bound shows that what if we allow +8? Can we get better than into the 4/3 bound? It turns out that we cannot. As long as we decrease the size by a little bit furthermore, the error has to grow, suddenly explode to some small polynomial. Okay, so that's basically a whole complete picture of additive spanners. +2, +4, +6, like step functions. And then the error suddenly grows to some small polynomial. Okay, that's basically the whole picture of the previous results on this. Okay, so by the way, there are two remarks I would like to make. First, there are a lot of best papers here. This, I think, is the best SODA student paper, and this is the best stocked 16 student paper. So if you want to, I mean, how many of your students, if you want to get a best student paper, I pick one topic from here. Okay. And these are spanners. What we have to do with sublinear ones. So I think the interaction of this talk and the general theme of the workshop can be probably slightly different from others, as we're not considering sublinear space or time or query. We're considering sublinear stretch. Okay, so the accuracy, we put some sublinear in it. So modificated ones allows you +4D, +6D, like this, very large error. And +2, +4 is our very small constant. There are a lot of things we can do in the middle. And sublinear ones are just measuring like what we can do in the middle by the different sublinear functions. If, for example, the original distance is d, then we allowed like square root of d as the error. This is what sublinear stretch means. And this will going to be the topic of today. Okay. And there are other kinds like mixed, where we allow a small, like close to 1 modificative factor and some plus beta additive factor. There are also like results on that, and it's not a topic today. So what we'll be studying is this type of sublinear stretch. What is the best size bound we can achieve? Okay. So there are also some previous work for, okay, it's interesting that it has been shown that only this type of sublinear terms are interesting. So there are also a step function shape of the complexity structure here. Okay, so if you want d to the 0.3, it's the same complexity as d to the 0.5. Okay, so only this type of stretch functions are interesting. And the bounds are also proved for them. So the first result by Sorup and Zwick says that we can achieve n to the 1 plus 1 over k. And then was improved by Pettie, saying that the additive factor is some exponential to the k here. The exponent is 3 over 4 to the k. So it's not growing as 1 over k inversely, but exponentially small with k. Can everyone clearly read this? Sort of it's a 3 over 4 to the k, and the Denominator doesn't matter, it's a constant. Okay. So is 3 over 4 the right constant here? It has been later shown that 1 over 2 has to be at least the lower bound. Okay, so for like getting this type of stretch function, the data structure has to contain at least n to the 1 plus 1 over 2 to the k plus 1 minus 1. But erase all this, it's n to the 1 plus 1 over 2 to the k. So the exponential dependence on k, the constant has to be at least 1 over 2, at most 3 over 4. What is the right constant there? Okay. Now our result is that 1 over 2 is the right constant. Okay. By the way, this lower bound also holds for any data structure. And we show that such upper bound, almost matching upper bound can be achieved by spanners. That is why we say spanners are near optimal, almost optimal distance oracles. Okay.
The results that you mentioned saying that the distance approximation 0.3 is the same as 0.5, those are not a function of constructions and so on, they are for some other reasons?
It's just their lower bound construction like gives you, if you do something better than that, you already give lower step.
It's not some reduction which says 0.3 can be.
Yeah, no. It's just I think it's probably similar to the question that Tony got earlier in the morning. It's like two curves, the closest point of them is, So it's a main result clear. Okay, so basically this is the result I'm going to talk about today. And I would like to mention a secondary result of this paper, which I think is also interesting regime. Okay, it's the linear size additive spanners. So there's no trade-off now. What if we require that the spanners contain only linearly number of edges? And we allow the error to depend on n, not only some function of d. How small can we get this Gn to be? Okay, just linearly many edges. This is also a very interesting regime with a lot of papers on them. Okay, so the lower bound has been improved by a sequence of papers to n to the 1 over 7 2 years ago. And the upper bound is being pushed by several works. And our work slightly get better than 0.429, we get 0.403 by complicated construction. And after our paper is actually 23. And after our paper, there's a new paper by a group of researchers, I think Virginia Williams included. They slightly improved the lower bound again to into the 3 over 17. Okay, so it's still 0.1 something, and this is still 0.4 something. Closing this gap will be very interesting. Okay. Next, best student paper, topic. Okay, potentially. Okay, this is just another interesting regime that I want to mention. Still, we'll be talking only about the sublinear additive spanner. Okay. So, is there any other question with the results so far? Otherwise, I will dive into the details a little bit. Yeah.
Is there any primal dual notion, like in the previous, like this problem? Is there a primal dual notion that you can just directly say, currently the way you got that the spanners are optimal, so proving they achieve the optimal bounds. But is it conceivable to prove that without even getting the optimal bounds specifically? Just say that no matter what algorithm you have, you can always turn it into a spanner, for instance.
I think you are probably mentioning the existential optimality of some greedy algorithm. You're mentioning some. Yeah. So. I don't think there's a sort of a counterpart here. So there, the scenario is the Eldridge-Gersh conjecture give you a bound, and that bound is what is achieved optimally by the algorithm. Here, it's just a bound. There, the bound is not closed yet, although people believe it. So here we know it, and I don't think there's any algorithm achieving the existentially optimal. It's just this algorithm. Yeah.
Basically, what you're proving is stronger than the message you said. No, you're proving this is the upper bound also.
Upper and lower bound are now close. So this holds for any data structure. We construct a spanner achieving the bound. Yeah. Any other question? Okay. Now let's start by looking at a special case, and that is really just illustrating all the ideas. Okay, so it's warmed up, but considering k equals 2 case, but basically the general case will just be 1 slide after that. Okay, all ideas are here. So do we still remember the bound? Here it's k equals 2. Okay, so it's 1 plus 1 over 2 to the k plus 1 minus 1. the 2 to the 3 minus 1, 7. 1 plus 1 over 7, 8 over 7. Okay, it's all bound here. Yeah. Do we still remember plus 6? Plus 6 is 4 over 3 here. So we are below that as we are allowing a larger error. Okay, just refresh our memory a little. Okay, so what we're going to do is to look at a specific D and construct like spanners for preserving pairs at distance equals roughly that D. Because we can only guess D by taking log-n layers. We forget about polylog-n factors, so we just enumerate for all D equals 1, 2, 4, etc. Okay, from now on, fix a D and only consider pairs at distance D. Okay. Let's make a first simplifying assumption. Assume that the graph consists of disjoint clusters of radius square root of D. Okay. And you're given these edges between clusters for free. You're only required to pick some edges inside cluster to be your spanner. Okay. Assume this is the special case. Why D to 0.5? This is basically the error we allowed. Okay. So basically, every pair inside it, as long as we construct a BFS tree, we preserve the distance like to our guarantee. Okay. So the first simplifying assumption, we have this disjoint clusters. We just need to pick the edges within the clusters, and edges between clusters are given to you for free. I mean, one thing we just said is we can do a BFS within each cluster. That takes no more than a linearly number of edges in total. Okay. And after that, every pair of vertices inside the cluster, we're done. Because the distance between them is smaller than square root of D. Okay. So yeah, right now we fix some D. So we just allow the distance error to be as large as this. Okay. Okay. So the problem is basically preserve pairs of vertices from different clusters. That's the only thing we need to deal with from now on. Okay. And actually, if we just do BFS, we need to start with some vertex, and that's called center of these clusters. From now on, we only need to preserve the center pair distances, not like any two pairs. Actually, it's enough to just preserve the center pair, because if we look at an arbitrary pair, if we have already preserved the center pair in the corresponding cluster, then as this is most square root of D, this is most square root of D, and this is the almost shortest path connecting centers, we can just use this concatenation to approximate the real distance. That's just plus some constant times square root of D, and that's okay with us. So only center pairs from now on. Okay, but there can be just many center pairs, so there are still things to do. Okay, so set of center pairs is actually, if you, for any vertex here, add a almost shortest path connecting them, you have also set of center pair. Although looks like you are settling an arbitrary pair, but they automatically settle the center pair as well, all because of the small radius. As long as you settle some pair, you settle center pair. Okay, so yeah, that's the first simplification and the first step in the algorithm. The second step is we can also make a second simplification. Recall that we are now dealing with pairs that are at distance D. We can now assume that the shortest path between them goes through about square root of D clusters. Okay. Each cluster has radius D, so it has to go through at least square root of D clusters. And now we are assuming that they just go through square root of D clusters. Second simplification. Now this number of bounds on the clusters will automatically decompose the shortest path by the first time and last time that they enter and exit a cluster. Okay, this we view as, for example, portals or terminals. Okay. If we have preserved these two vertices, and this two, the first and last segment, then we have basically preserved the center pair. Okay, preserved meaning if we preserve these two vertices to within a factor of constant, then accumulatively it goes through square root of n clusters, each incur a plus constant error, then the total accumulated error is square root of n as well. Okay. And this is actually a thing we know how to do. We just plug in a +6 spanner within each cluster. So that if we look at the real shortest path and look at the entrance exit pair, we know that this pair is preserved within error +6. Now, accumulatively, we have incurred at most square root of D times 6, which is O square root of D. Any questions so far?
Sorry,
Yeah.
this is a minor question. Is there anything special about 6 here?
6 is sort of the best we can get, the best size we can get for a plus constant error. So previously +2, +4, +6, 6 is smallest. We want even smaller the size blow. We want even smaller size, the error blows up.
I'm not undirected spanners, but if you go for a bigger constant, it doesn't become easier?
Yeah. So anything bigger is the same as 6, unless you go to some small polynomial. Yeah. Yeah.
You said that the radius of each cluster is root d.
Square root d.
But maybe you don't spend root d distance inside each one. So
Yeah.
the number of clusters you go through could be more than
Yeah.
square.
So this is our simplifying assumption too. We assume that they just go through square root of d. Yeah. So it gets into a little bit detail, so it can be confusing. Please feel free to ask questions. Yeah. So yeah, this is basically a recall of previous result. +6 we can do in small size. Okay, but how small? So +6 spanners inside this cluster has sides, a number of vertices in this cluster to the 4/3. So we still pay overhead. But as long as all these clusters are small, we're okay with not paying too much overhead overall. Okay, so when all the clusters are small, we're done. Small, how small? Smaller than n to the 3/7, because this term to the 4/3 is n to the 4/7, which is a plus 1/7 overhead here. Okay. Everything on this slide, okay? As long as all the clusters are small, we're done, because we plant a +6 spanner inside it, and the total size will be bounded. Okay. Yeah.
Did you tell us how you find these clusters, or just assume?
So this is all simplifying assumptions. Assume we are given the clusters. Assume every shortest path pass through this number of clusters. Yeah.
Maybe I'm missing something, but where does the N4/7 come from? Like
Okay. So this is in order to make sure that this bound is governed by 8/7. So if you make it smaller, this makes smaller. But eventually there's a trade-off, and this is a point we break.
And the N4/7, like the number of clusters or
Size of a cluster, size bound of a small cluster. So as long as each of these clusters contain no more than n to the 3/7 vertices.
there are two N4s. Like if I'm trying.
Okay, this is the number of clusters. This is the size to the 4/3.
The first factor is number of
Number, yeah. So the total size eventually we want.
So you assume C is n to the 3/7, not upper bounded by n to the
Upper bounded by. Because if it is even smaller, the overhead is even smaller.
But if C is a smaller, how do you get n to the 4?
Yeah, so the sum of them, each pays a smaller overhead. That I mean? Yeah. Yeah, only helps. Yeah, this is, yeah. They're trying to illustrating that 8/7 is the point we break here. Okay. Yeah. Yeah, we still got time. I think welcome many questions as long as it helps. Okay. So now we only need to handle large clusters. Small clusters are handled by +6 spanners inside it. Okay. Large clusters. Assume the green ones are large clusters. So first, the size of large cluster is larger than n to the 3/7. So the number of them cannot be too large, at most n to the 4/7. Okay. And then previously we want to plant a +6 inside each. But right now, as the size of it is large, so the overhead we pay may be too large. So we don't want to do that. But we actually can observe that a +6 pairwise spanner is an overkill. It preserves every pair of distance to within +6. We don't need every pair of distance to be preserved. For example, recall that we only need to preserve center-center pairs, and this is the portal they give us. We only need to preserve for the portal formed as demand pairs, the demand pair distance to be +6. Okay, this is a significantly simpler task than all pair distances. Okay, maybe the size is large, the number of pairs is very large, but we only need to preserve a small number of pairs. That does not require a global spanner. Okay, so now what we do is just figure out what pairs we want to preserve and only preserve them. This is how we get to get around this +6 spanners inverted. Okay, so assume that, so the algorithm is basically run over all center pairs. For every center pair, find the real shortest path. Look at how many other large clusters it goes through. For each large cluster that it goes through, find the entrance and exit pair. Mark this as a demand pair for this cluster. So that each cluster collects a lot of demand pairs. And then it constructs a spanner for preserving those demand pairs. Okay, that is the algorithm. Okay, so we just want to bound the number of demand pairs it needs to preserve. It turns out it's significantly smaller. Okay. Okay, so yeah, that's basically the algorithm. And once we have processed a XW center pair, all the clusters that the shortest path goes through will be marked as settled with X or settled with W, because a almost shortest path has already been inserted. Already not inserted immediately, but we set up the tasks for them to be later handled. Okay. We give them demand pairs. We are guaranteed that they will handle this demand pair later, so we view them as this is already settled because they will be done in the second phase. So we basically view that there's already almost shortest paths connecting them, and they are settled. Because later on, if we just handle another pair and found some cluster on this shortest path is settled with both X and W, we will do nothing. We will not give any new demand pairs because this pair has already been sort of secondarily settled. They're both settled with someone in the middle. They are already almost preserved. So what this means is that every time a cluster gets a new demand pair, it gets settled with a new cluster, big cluster. Therefore, the number of demand pair it gets eventually is bounded by the number of large clusters. Okay, so we process in rounds. Every round, a cluster gets a new demand pair, but only when it gets settled with a new large cluster. So the number of demand pair it collects in the end is at most n to the 4 over 7. Okay, so number of demand pairs we preserved inside it is at most n to the 4 over 7. So recall its size is at least n to the 3 over 7. So number of pairs is n to the 6 over 7 at least, but we only preserve n to the 4 over 7. Okay. This is actually, yeah, each cluster. Okay, but do we have really an advantage of this? Because there is a previous result saying that if the number of pairs is small, we can do better. Okay, so previous result by Kavisa says we can build a +6 pairwise spanner, preserving only pairs of size n times p to the 1 over 4. This is pairs. Okay, here this is n to the 4 over 7. Now 1 to the 4 of it is n to the 1 over 7. This gives us the balance n to the 8 over 7. Okay. Okay, so yeah, just one line of calculation. I mean, there's still the similar calculation. Okay, if each of them has demand pair bounded by this 4 over 7, then to the 1 over 4 is n to the 1 over 7 overhead. So in total, it's n over 1 over 7 overhead. Okay, that's it. That's the special case where k equals 2. Okay, so any question on this slide?
Still the pending simplifying as option, right?
Yeah, still pending. Yeah, I will sort of convince you how to do that in the very end. So looking at the roadmap again, what we have done, we have made simplifying assumptions saying the graph consists of disjoint clusters, and every pair of vertices that we want to consider, they pass through a certain number of clusters. So with this assumption, the first step is build BFS inside these clusters. Second step, build +6 spanners in each of the small clusters. Third step, handle large clusters by considering all pairs, all center pairs, and give them demands, so that later each cluster, together with all the demands it collects, build a pairwise +6 spanners in it. Okay. This is the whole algorithm.
So what happens if there is a omega n size large cluster
Is
which has close to n square pairs?
so if you mean the whole graph is a cluster?
That could happen. I mean, that's not ruled out. Probably.
Yeah, so it still gets only a small number of demands. So it's yeah, if you think like the whole graph is a cluster, then basically we don't do anything because the radius has already been the error we tolerate.
No, I mean, if n over 2 vertices which form a cluster in the middle, and if I look at all the pairs, portals which are created,
Yeah.
why can't that number be omega n?
Yeah, there are not very many numbers. There are not very many demand pairs you get, because every demand pair, you get it from some pair of large clusters. And if you are just 2 clusters, you don't get a pair of large clusters, many pairs of large clusters to deal with.
So what about the edges between the clusters, the bridges?
Assume they're given to you for free.
For free?
Yeah, for free. You pay nothing to include all of them in your spanner. So yeah, all the simplifying assumptions and these edges are given to you for free between clusters, are handled in the previous work by I think Virginia Williams and Greg Baldwin. Okay, basically there's just one more slide for general cases. So yeah, if you have questions, it would be good to ask now. Okay, so the general case, oh yeah, this is actually, there's a name for handling large pairs. It's called path buying. So our buying passes. For every center pair, we find a path and we want to buy this path, but with demand pairs. So it's like you are using your credit card, you pay credit to get food, and later on you pay the credit card, pay cash to the credit. Okay, is that you sort of yeah? So the demand pairs is sort of a capital in this algorithm. Okay, so this is called path buying, and this term has been coined early before us. So basically, as clusters and planting small spanners and path buying, they're all like techniques used in the previous work. We just combine them in a slightly different way to achieve the optimal stretch. Okay, so that's basically it. For the general case, this is our general stretch 1 minus 1 over k in the exponent, and the bound is like 1 plus 1 over 2 to the k plus 1 minus 1. So we still like do this clusterings and plant a spanning tree in each of the cluster. But right now, the radius is different. The radius is always set to be the error, okay, because whatever happens within this radius is accepted. Okay. So we still allow that, like we still make simplifying assumptions that every pair they want to handle just goes through the minimum number of clusters it should. So they're at distance d, and now each cluster has radius d to the 1 minus 1 over d. So now number of clusters they go through is d to the 1 over k. Okay. So number of clusters that go through is d to the 1 over k. The radius is d to the k minus 1 over k. Now inside each cluster, we don't ever need a plus 6. We only need OD to the 1 minus 1 over k minus 1 pairwise additive spanner inside it to eventually get our whole spanner. Okay, so plus 6 here is now significantly relaxed. We only need 1 minus 1 over k minus 1, which is k minus 2 over k minus 1. This is because we just look at this term. This is the radius. Okay, this is the max distance, and to this third exponent, we will get d to the k minus 2 over 2. And this is the number of clusters that it goes through. So the cumulative stretch is the product of these two. It's d to the k minus 1 over k. Okay, this is just calculation, but the only point is that we don't need plus 6 pairwise spanners in each cluster, but we can tolerate an even larger pairwise spanner inside each, and therefore we get a smaller overhead. This is basically what happens in the general case. Okay, so yeah, and we need to also show that there exists such smaller pairwise spanner like the previous Kavisa's result. Plus 6 n times p to the 1 over 4, we show something similar. Plus d to the 1 minus 1 over k minus 1, we show n times p to the 1 over 2 to the k. So before it was k equals 2, so n p to the 1 over 4. We generalize basically to general k. Okay, and that eventually gave us this bound. Okay, BFS, insert spanner, path buying. Okay, overall, the whole picture is this. We consider the special case where k equals 2. Then we use the Kavisa spanner to do path buying, and we get 8 over 7. But we need to generalize for general k. Therefore, we do some advanced path buying and all the way by inductive proof get pairwise spanner result and use each of them to give a general like stretch size trade-off that we have described. Okay, so this is one path buying step. This is a slightly different path buying step, more complicated. We first need to get here and then get here. Okay, so yeah, that's basically it, the whole framework of the general algorithm. There's no like subroutine that is completely new from previous work. All are there. It's just they are not done in this inductive way, which eventually turned out that we can get optimal sites. Okay. Yes. Yeah, so that's sort of somewhere we have cheated before, but next slide. Have cheated too many times. Okay, yeah. So yeah, it's actually just there's one lemma with one page proof that achieve all of them. Any other question? Okay. So yeah, so where I have cheated, destroying clusters. Each pass through some number of clusters. Okay, I mean this is all handled in the previous work, roughly 8 years ago by Abboud-Bodwin and Zihan Williams here. So actually, it cannot assume that all the balls are disjoint. They can overlap. Okay, but the total size of them is still O of n. Okay, so the algorithm is sort of each point it grows balls to a certain radius. Now every center has a ball, and we collect it. We just pick a subset of them such that this is guaranteed. It's sort of not a sort of technical part of the argument. It's one page. Okay, so there's actually a third, but sort of that part is in the advanced pass buying, and sort of omitting that part out of this talk due to the time limit. Okay, so summary is we get near almost optimal sublinear additive spanner, whose definition is when the original distance is d, we allow d to the 1 minus 1 over k as an error. Okay, and the size is n to the 1 plus 1 over 2 to the k minus 1 plus 1. This is sort of a weird dependence. You don't see it in many other places. N to the 1 plus 1 over k probably see in many times, but 1 plus 1 over some exponential to the k. Okay, this is not very frequent as far as I know. Okay, and it matches the lower bound holds for all data structures. That's why we say spanners are almost optimal distance oracles in the size stretch trade-off. Okay, that's a summary of the result today. Open questions. What about making this almost near, or just nothing here? Okay, so removing the until little one term. Specifically, what we have shown is it can be any small constant epsilon, and epsilon need to be have some dependence here. Okay, so making epsilon maybe polylog log n is just unto a little one. Okay, so how to remove them is interesting open question. And also the linear size regime, which is if we want the spanners to just have linear number of edges, how small can we get the error to be? G of n, n to the 1.7, n to 0.17, n to 0.40, etc. What's the right answer? By a student paper. So that's all I have. Thank you.
Questions for Zihan?
So can you remind us what happened? You said that the edges between the clusters are given.
Yeah.
But we wanted to remove that assumption, right?
Yeah. So the balls are overlapping, and edges are all contain them. So it's not like intercluster edges. There are no such thing. Yeah. Yes.
Have you thought about what happens to this if it's a directed graph instead?
Yeah. So very good question. I think directed spanners I think it's the topic of the next talk. Are
are there specific procedures here which you can also run in the directed thing?
So BFS, yes, sometimes there are infinite distance in the graph. So I think it's fundamentally different, and should be harder in the sense that the bounds are higher. Not sure if it is the technical harder. Yeah. So there are many hardness results already proved.
Yeah, I just want to know if the approach can be repurposed somehow with some, wrappers and stuff to be directed.
Yeah. So we have
worse, but can the underlying approach be used somehow?
Yeah, we haven't thought much. Yeah, honestly. Yeah. So I think some definitely requires undirectedness here. Like you preserve a pair, and you say that any close by pairs are also preserved. You need distances in both ways, and distance between these pairs to be preserved also in both ways. And
Yeah, I think the clustering procedure itself might.
Yeah, clustering too. Yeah.
Thank you so much.
Any other question?
So, just, was there a well-known sort of clustering algorithm you use, or could you say a few words about that?
Yeah. So each point grows a ball around it, starting with radius square root of d, if that's the r you pick, and then go to 2D, 4D, etc. When some size increases small, you stop. Some sort of a ball cutting algorithm, but different from the one you see in the sparses cut, etc. Okay, ball growing argument, if that's a three-word summary.
All right, let's thank Zihan again.
Thank you.